So we will essentially spend the rest of today studying surjectivity, injectivity, and the relationships of the two. So for the rest of this lecture, let's fix SEA. And again, I suppose you all can guess what does it mean for SEA to be surjective or injective. So A is injective if F is injective, A is surjective if F is surjective. And lastly, we call a configuration C a Garden of Eden if it has no preimages So yeah, this is a poetic characterization of the fact that such a configuration can only exist at the beginning of time and no later. And the first topic we will discuss is that, well, obviously, SCA is surjective if and only if it has no Garden of Eden configurations. So Garden of Eden configurations, which seems to be a pretty exhaustive property to check, which is quite global, but we will see that actually surjectivity, or let's say non-surjectivity, is already witnessed by some local patterns. So let's define what are local patterns. So let D be a subset of Z to the D. And so yeah, okay. A pattern P is a tuple where P is just an assignment of each position in the domain D to some state S. Yeah, so it's pretty clear why it's called a pattern. Like, for instance, if this is 0, 0, this would be a pattern in some two-dimensional CA, right? So we say that P is finite if D is finite and lastly we say that a configuration C contains a pattern well, maybe intuitively you would say if the restriction of C to the D is the same as P, but we will make it more general. We want C to contain this pattern up to any translation, which also makes sense. So if there exists some shift vector such that the shifted form of the configuration restricted to D is exactly P. And lastly, we say that a finite pattern is an orphan if every configuration that contains it is a Garden of Eden. So in some sense, the orphan is a finite witness of non-surjectivity. As long as we have it, any configuration that contains it cannot have a preimage. And I think it's already time to essentially show the following. A is surjective if and only if it has no orphans. So this is really where the local property of surjectivity comes in. So clearly, if it is surjective, it does not contain any, or like if it has no orphans. So if A has an orphan, it's clearly non-surjective because any configuration containing it is Garden of Eden. So what we want to show is that if it has no orphans, it is surjective. It is surjective, yeah. So, suppose for contradiction, the existence of C, which is a Garden of Eden. Essentially, the argument will be pretty straightforward. We will look at the finite patterns in the regions, in let's say larger and larger regions of this configuration. And since none of these are orphans, there will always exist some preimage. And these preimage sets will be closed. We just take their intersection, and this will be non-empty. It will contain the preimage of C. What is the best way to write it down? So let Cn be exactly this. So all configurations that agree with C on this region. And I don't know. and let Kn be the pre-image of this. So claim is that for each n, Kn is a closed, non-empty set. So it is closed because this ball is closed and f is continuous, so it maps the closed set onto a closed set. So this is clear. And why is it non-empty? Well, if it was empty, then the restriction of C to this would be an orphan. So hopefully this should be clear. So next, clearly if we take the sequence of these closed sets, it is decreasing because we are more and more demanding. We want the pre-image, or we want the set of configurations whose image matches with more and more of C. So from, it's not here anymore, but I think it was point 2 of the list of properties of a compact metric space. Yeah, there exists a configuration that is in the intersection of these Kns. So we want to show that f of this C star is actually C. And that should be pretty clear. We will just verify it at an arbitrary position, and whatever vector we pick, it's gonna eventually become a part of one of these regions, and then because C prime belongs to the set Kn, it will match with its image will match with C on that region. Yeah, so let V be an arbitrary vector. So since there exists n such that V is a member of this box, and C prime is a member of the nth set Kn, we have yeah. So indeed, this is a pre-image. I think a slightly more detailed explanation is in the lecture notes, but hopefully it's clear. So that's nice. First of all, if we want to show that a CA is non-surjective, it gives us this local criterion. We just have to find an orphan. But in general, this is quite difficult. Even if the CA you are given is non-surjective, exhaustively going through all the finite patterns and checking all their finite pre-images is tough. For instance, Game of Life is not surjective, but the smallest known orphan is contained in a box of some size 8 times 12, so it's quite hard to check all its preimages really are not leading to it. So there's actually more practical criteria of non-surjectivity we will discuss now. But maybe this is a good time to pause and think about von Neumann's universal constructor, where we had this problem which I was mentioning, is that not every particular finite pattern is constructible in the by the self-replicator. For instance, if you have a single active arrow surrounded by all zeros, or all by the quiescent state, this just cannot exist at any time later than 0. So the universal constructor has some physical limits on what kinds of patterns it can construct. And now we know that the reason it cannot construct this is that this pattern is exactly an orphan for the von Neumann CA. And so in some sense, it's not like we are formalizing what universal constructor means, but at least we have some hard bound on the fact that each universal constructor can only construct patterns that are not orphans. Essentially, they should be able to exist at any time step. So, yeah. So maybe it's nice to keep that in mind. And the second criterion for non-surjectivity, or for surjectivity, is called balancedness. And here it's maybe nice to start with an example, which already illustrates almost everything. So the example is as follows. We will discuss rule 110, which is one of the most compact CA examples you can have. And we will show that its rule table is not balanced, and this will already lead us to conclude that the CA is non-surjective. So how will this work? So rule 110's rule table is in some sense not balanced. Is not surjective. So I need some more chalk for this. So let's just draw the rule table of rule 110. To see so this corresponds to 0, 0, 0. This corresponds to 1, 1, 1. To get rid of the color inversion problem. So rule 110 does not fit 128, but it does fit 64, and it also does fit 32. So now we're at 96. So it still fits 16. So 96. No, it does not. Okay. But it does fit 8, 104, and it does fit 4, and it does fit 2, but it's even. So this is the rule table. And as you can see, there's the number of entries that are mapped to 0 is only 3. And the number of entries that are mapped to a 1 are 5. And this imbalance, we can already use it to show that the CA is not surjective. The strategy we will be using will be somehow the same all over again. We will amplify this imbalance, and we will use some kind of counting argument to show that there is not enough preimages for certain finite patterns. So the image, I suppose, should be something like this. We can look at all finite dimensional patterns that have 0, and the preimage of that will be some triple. So here we we don't care. We will say there can be anything. And then here will be another triple, and here will be another 0. So essentially, these are some finite patterns we will consider, and we will impose enough zeros to essentially say that the number of preimages of this set will only be limited due to this imbalance. So let me write it down properly. So let Ck be the number of finite patterns. What is this? If this is 3 times k, then this is 3k minus 2. Because if we want to map this pattern onto this pattern, then yeah, we have to subtract twice the radius. So let Ck be the number of finite sequences from 2 to the 3k minus 1 such that u at position 0 is the same as u at position 3 is the same as u at position, actually at position 2, no 0. 3k minus 3 is 0. So what are the number of candidates of these finite patterns that are, let's say, longer by 2 cells that would map onto these? So here is where we can notice that, okay, for each of these triple that maps to 0, we only have 3 candidates, right? So let's say the number of patterns of length 3k which map to a pattern from Ck is at most 3 to the power of k, right? We have 3 options for each triple, but the size of Ck is 2 to the 2k minus 2, so 4 to the k minus 1. And now it simply is enough to amplify this imbalance enough, like to consider k, okay. It suffices to essentially take k large enough such that, yeah, this is larger than this. It suffices to take k large enough such that 3 to the k is less than 4 to the k minus 1. To have a guarantee that the set Ck contains an orphan. So hopefully this is clear. So do you think it is enough for the rule table to be balanced in order for a CA to be surjective? The answer is no. Our life would be too good. That would be too simple of a criterion somehow. So let's look at the second example. So rule 184, which is sometimes called the traffic rule, we will see why, has a balanced rule table but is still not surjective. So how we can interpret rule 184 is essentially each black square you can interpret as the presence of a car. And the car always wants to move to the right if there is a free spot. So what would be the outcome of this? If it does not have a free spot, the car just waits. So here the central car cannot move, so it waits. Here it can, so it's empty because this car is waiting, so nothing gets moved here. Here this car moves here because it has a free spot, so it's black. Here also, here the car is waiting, so it's still black. Here it moves. Here there's no car to enter the picture, and here also not. Yeah, so I don't know. If we have a configuration its image, for instance, of this would be, and let's say everything is zeros. So this is empty, the car moves here. Here this is empty because this car moves here. This car is waiting. This car moves. And that's it. Is it clear? Great. So as you can see, now we have a balanced, so the local rule is a Boolean function. The notion of balancedness is standard. So it has the same number of, or like if you take the number of inputs that map to 0 and that map to 1, the number is the same. But it's pretty, it is easy to verify. It is easy to verify that, let me think, I think, yeah, one of these is an orphan. Yeah, probably this one. So let's just try to brainstorm why this could be an orphan. So if it had a preimage, what could happen? So this one could have either come from a waiting car, but that is not possible because there's 2 zeros, so there is no way there could have been a car here that would make this car wait, right? So this one had to come from a moving car, but in that case, this one also had to come from a moving car, but that car would have waited, so yeah. So clearly checking the rule table is not enough, but there is some notion of a balanced local rule that is enough to characterize surjectivity, but we have to unravel the local rule to not only work for the minimal configurations given by the radius, but for arbitrary finite patterns. So we're now just gonna do this. So unraveling a local rule. So So suppose A has a local rule F, its unraveled form F tilde maps for each, let's say, K, and each domain D, which will be just the box of size K, so something like this. Patterns okay, this will be, let's say, the output will be patterns with this domain. So what will be the input patterns? We have to make this box larger by the radius. Patterns like this. Or let's say patterns of the form two patterns essentially like this, as follows. So F, if it got this kind of input pattern, essentially does the same thing as a global map of some configuration C restricted to the domain D, where C restricted to D prime is exactly B prime. I really found no better way to define this. It might sound a bit confusing, but it's extremely natural. Let me show you the let's say the visual for this in dimension 1. So in 1D, let's say we have a local rule with radius 1. So this is the image to see under that, right? F local rule with radius 1. And now suppose you want to have K consecutive outputs. So you have to exactly consider patterns. So in 1D it's nice to somehow unite the patterns with finite words. So this is just a sequence of K symbols. And essentially this is what F tilde does. It takes the pattern with a larger domain, which is exactly enlarged by the radius to each sides of the cube, and it takes it to a pattern which is now just this cube of size K by essentially applying to every triplet the local rule F. So there's nothing to it. But now we can define what balancedness means. So we can see that, yes?
B prime is to the power B, or?
Ah, yes, of course. Yeah, thank you. That's an interesting typo. Okay. Any more questions? Wonderful. So what we can notice is that for each k, f maps the set S to the k plus 2r, let's say, into the set S to the power of k, okay, to the power of d. We're still in d dimensions. So these are all the patterns with the domain minus r2k plus r minus 1 to the power of d, and these are all the patterns with domain, which is the box, which is a d-dimensional box of size k. So on average, each pattern from S to the k to the d has how many pre-images? Just S to the k plus 2r to the power of d divided by S, so basically minus k to the power of d pre-images under f tilde. And now we literally just say that SCA is balanced if indeed every pattern has exactly that number of pre-images. So for k equals 1, that is characteristic of a balanced rule table. And for larger k, we have to unravel the rule and count the number of outputs for each input configuration pattern. So we say that A is balanced if the number of pre-images of each such pattern is exactly this number. So what happens in one dimension? In 1D, we can view or we can identify each pattern P from 0 to k minus 1 to S with a word u from S to the power of k, just by u is exactly p0, p1, pk minus 1. And a 1D CA is balanced if each finite pattern has S k plus 2r minus k is just S to the 2r pre-images. So this is a special property of one dimension, that the number of pre-images of a pattern does not depend on the pattern's size and is always just the size of the state set to the power of 2 to the r. So here is a second criterion if you want to prove that SCA is non-surjective. You just have to keep unraveling until you find some imbalance. So we can now prove that. So proposition A is surjective if A is balanced. So we will prove this only in one dimension, but not that it would get exceptionally harder in more dimensions, just the notation is much easier. But you can find the general proof either in the notes of Jarkko Kari that I strongly recommend in the lecture notes, or you can prove it as an exercise. It's really not that difficult. So yeah, so essentially if A is balanced, in particular, every finite pattern has at least one preimage, so A cannot have orphans. And in the opposite direction, if A is not balanced, then there exists some finite pattern of some size k where the imbalance first shows. So in particular, such that the number of preimages of this finite pattern is less than the average. So since there's imbalance, there at least for one there has to be fewer than the average, which is s to the power of 2r. And now the proof follows exactly the same tactic as for rule 110. So now follow exactly the same strategy as for rule 110. Essentially, we want to amplify this imbalance. So what you would do is you would create some smart set of configurations which contain U in a lot of positions, and you would then look at what is the possible number of finite patterns that are preimages under F tilde, and you would realize that because each finite block has this constraint, it would lead to to essentially having more patterns here than here. So one particular finite pattern would not have a preimage. So to construct an orphan. Mm-hmm.
So here in the example of rule 184, the notion of balanced we have described here is not the same thing as the one we described here.
Yeah. Well, that's exactly what I was saying. If you only look at the rule table, it's as if you looked only at the balancedness of F tilde for k equals 1. So here the output patterns are size 1. But what you would have to do then is unravel it for k equals 2. So you should then look at all the tuple outputs which have sequences of size 4 as preimages, and you would have to check that each of these tuples has the exact same number of preimages. And if it does not fail there, you would have to unravel more and more and more. So the last characterizing criterion of surjectivity is pre-injectivity. So, definition. So, we say that two configurations are asymptotic if they only differ in finitely many positions. That's pretty, we say that. If the number of positions where they differ is finite, and we say that a cellular automaton is pre-injective if it is injective on the set of all of its asymptotic configurations in some sense. So we say that A is pre-injective if if for every two asymptotic configurations C1, C2, it holds that. If they are different, then their image is also different. So a very easy observation is that injectivity is a stronger property. Injectivity implies pre-injectivity. That's pretty clear, hopefully. And now we are ready for the grand finale. So the Garden of Eden theorem. It would be great to have one more blackboard, but we do. Let's try to figure it out somehow. Okay, so A is surjective. If and only if it is pre-injective. Nice. So let's start with whichever implication. I think I will still need more space. Is it okay if I delete this blackboard? Is there anyone who protests? Yeah, I should ask questions like this. Great. So suppose that A is not surjective, and we will show that it is not pre-injective. So again, I will show the proof in dimension 1, but here there is really nothing to the generalization. It's just a notational convenience. So there exists some orphan for some n. And we will use this existence to construct two asymptotic configurations that collide. So there is only one theme to all the proofs that I show you today. It's always some kind of amplification of something and a counting argument. So we will use it yet again. So in this particular case, suppose, or I will draw the following image. Suppose I look at finite patterns of length n times k. So let's fix some k. And I fill the rest. So, okay. And let Q be some arbitrary state. So, suppose, okay, actually I should draw this shorter. So suppose this is a block of length nk minus 2r, and everything else is filled with this state q. So what is the image of that under f? So from some moment onwards, there is the repetition of some potentially different state q prime. That starts happening whenever the local rule only sees the state q everywhere on its input. And then there is a part, and again a finite one, which potentially has something else. And because of the radius, this increases on both sides by r, right? So yeah, this is exactly the counting argument. So we just have to formally write it down. So the mission will be like this. We will count all possible configurations of this form. There will be s to the power of nk minus 2r of them, right? And if we look at their images, here there will be, this is where the orphan comes in. Essentially, we know there is an orphan of length n. So for each of these chunks, we have only s to the power of n minus 1 options, right? The u cannot ever appear there, otherwise it would have a preimage. So the number of configurations of this form is this, and the number of configurations in its image is at most s to the power of n minus 1, and we have k of these, so to the power of k. So this is a great moment to stop and prove a lemma, which will help us to essentially, so what we want claim is that there exists a large enough k such that there is less potential candidates. There is more potential candidates than there is images. So is less than s, the size of s to the power of nk minus 2 r, which means that there must exist two asymptotic configurations of this form that will collide. So we just have to prove the claim. Oh. So let me state it clearly as a lemma. So our lemma will say that for every d n and r positive integers, there, oh, and s, I forgot the number of states, great, there exists k such that, and exactly what we want there, so s to the power of n minus 1 to the power of k is less than s to the nk minus 2r, but let's prove this in arbitrary dimension, so that my claim that the generalization to arbitrary dimension is straightforward. Let's prove this lemma in the full generality. That's not going to be too painful. Great. So for s equals 1, it's clear. Since this side is 0 and this side is 1. And if s is larger than 1, then we can apply log of the base s to both sides. So we have this holds if and only if this holds. Yeah. To the nk minus 2r to the power of d. So let's just massage this. So this is k times log s of s to the power of n minus 1. And this is just nk minus 2r to the power of d. To the power of d, to the power of d. Now let's divide by k to the power of d. And we have the following. So n minus 2r over k to the power of d. And now this is a fixed constant which does not depend on k, and it is clearly less than 1. Clearly less than n. This, as k goes to infinity, approaches, yeah, there should have been also d here, I'm sorry. Yeah, this is the correct d-dimensional statement. Yeah, because now the pattern has, the orphan has, let's say, is a box of size n, so yeah. Whereas this is approaching n to the d. So yeah, clearly we just pick k large enough such that this overgrows this constant, which does not depend on k. So this means we're done with one implication, and let's roll on with the second one. Are there any questions? Okay. So let's also do the following. So suppose A is not pre-injective. We show it is not surjective. And again, the strategy will be very similar. So if it is not pre-injective, it means we have two configurations C1, C2 that collide under F and that are asymptotic. So it, like without loss of generality, we can pick a large enough domain D such that they agree everywhere outside of D, right? But not only that, I would also like them to agree on the section which is to ourselves to each side from the domain. And then we can call this finite pattern, for instance, U, or we can call it P1, okay, and we can call this P2. And here is the logic behind choosing this. Is let's say now these two blocks, these two patterns, P1 and P2, they can be used as interchangeable puzzle pieces. Like whenever you have a configuration that contains P1 and has some image under F, you can completely exchange P1 by P2, and it should not change the image under F. Why? Because everything here you keep the same, and P1 here had some 2R states that are exactly the same as P2. So clearly you cannot mess up anything outside. And inwards, this is because of the collision of the two configurations. So we will somehow use this to show that there cannot be enough pre-images for some patterns and that there exists an orphan. So let C1 and C2 be two asymptotic configurations such that they collide and let D be an interval of size n such that for D prime, okay, so this is some, I don't know, k plus n. If we take D prime to be k plus 2r, k plus n minus 2r, it holds that C1 and C2 agree everywhere outside of D prime. Yeah. So what happens now? We will do the following trick. We will again compose a bunch of finite patterns, now of length n. And we will look at their images under F tilde. So let's say there are k of these, k blocks. So this is a pattern of length k times n. And this image will have length k times n minus 2r. Right? So these are from S to the kn, and these are from S to the kn minus 2r. So now here's the trick. Imagine a finite pattern which does have a pre-image. You can kind of look at what are the blocks, consecutive blocks. This will be some u1, u2, up to uk. Each of these ui's is a block of length n. And whenever any of these ui's is equal to p1, you can exchange that block p1 with p2, and you will not lose the fact that this configuration is a preimage of the pattern you chose. So what this means is that every configuration that does have a preimage has a preimage consisting of blocks that can completely avoid p1, because whenever you see it, you just choose a different preimage which has p2 instead. So this leads to the following. There's still not enough blackboard. Amazing. Let's try this. It's really deep. It's a bit awkward. So essentially, this means that every, can you see here? No? Yeah, I don't like that part. We can probably erase this. So every pattern W from S to the kn minus 2r for every pattern, if W has a preimage under F tilde, it has one which does not contain P1. So yeah, formally P1 is just C1 restricted to D, P2 is C2 restricted to D, and from our informal discussions you can exchange these in a configuration without violating the image. So it has one that does not contain P1. So every pattern from S to the kn minus 2r has a preimage from the set Ck, which is just a concatenation of U patterns where each Ui is from S to the n but not P1. So the size of Ck is exactly S to the power of n minus 1 to the power of k. And again, we can use the lemma. We have a guarantee of the existence of some k such that this number is strictly less than the number of patterns for whom we're trying to find a preimage. So therefore, at least one of the patterns in this set is an orphan. So that's it. Yeah, it's just counting. The argument would go exactly the same in higher dimension. You would just draw two-dimensional boxes instead of one-dimensional blocks. So now we can finally observe that a game of life is not surjective. as if you take a grid consisting of only zeros, and if you take a grid consisting of only zeros and a single one, these are two asymptotic configurations that collide because this cell will die. So game of life is not pre-injective and not surjective. So let's just summarize the result. We can state this as a theorem. So injective CA already implies, okay, let me write it like a human, surjectivity. Since injective implies pre-injectivity and pre-injectivity is equivalent to surjectivity, which also means that injectivity is already equivalent to bijectivity, because each injective CA is also surjective and thus bijective. And thus equivalent to reversibility. Yeah. So I will show you probably next time an example of a CA which is surjective and not injective, such that you know that it really is a stronger property. But for now, I think you really deserve a break. Yeah.